All right, so we're starting class by taking a look at a little bit of factoring practice. It's good to bring this back a little bit, partly because it's also going to be coming up here very soon, but also because yesterday we did a decent amount of work with solving quadratics again, and we solved a number of them by square root principle. And then you did some, especially on the assignment last night, using quadratic formula. So yes, it's good to also bring back the whole factoring process. So, of course, factoring is where we have to look to see what two numbers add to the middle number and multiply to the last number. Like, for instance, if I gave you a separate problem over here, which, yes, I want to do in this case, like x squared plus 5x plus 6, we'd be saying what two numbers add to the 5 and multiply to the 6. So, adding to the middle, multiplying to the last number. And I wanted to remind us of that because looking at this one, we only have one number. We don't have two. So that negative 9 here, is the negative 9 that the number that we're adding to, or the number that we are multiplying to? Multiplying? Okay. How would we know? What tells us? Yeah, notice that one thing that's distinctive about this 9 here is that there's no x on it. It's just the number. The same thing was true about the 6 out here. And so that's why, yes, that's the one that we're going to be multiplying to. So we're going to be trying to multiply to a negative 9. Well, if we multiply to a negative 9, what are we adding to here? Yeah, 0. The only way that x goes away is if we multiply it by 0. So then, we're going to be writing it in our factored form here, where we have x plus or minus some number and x plus or minus some number. What are those two numbers that add to 0 but multiply to negative 9? 3 and negative 3, exactly. And so we get 3 and negative 3, so it's going to be x plus 3 times x minus 3, and yes, that is our factored form, because notice, they do add to 0, and they multiply to the negative 9. Excellent. All right, looking at the next one then. We are going to try to figure out which two numbers in this case are going to be adding to 0 and multiplying to negative 49. Is there such a combination? Yeah, there is. 7 and negative 7. And so then this is going to be our factored form here. All right, on to the next one then. Here we are going to be adding to 0 and multiplying to a positive 4. All right, is there such a combination that does that? All right, so would 2 and negative 2 work? What's 2 plus negative 2? 0. Yeah, okay, so that would give me the 0. And what's 2 times the negative 2? Negative 4. But of course, the negative here is a bit of a problem, right? Because this one's a plus. So 2 and negative 2 wouldn't quite work. Well, could I then shake it up? Could I then make it like, what about just 2 and 2? Could I just do 2 times 2? That would give me the 4, right? Would I still add to 0 then? No, then that would no longer add to 0. That would add to 4 instead. And so you notice we're running into a little bit of a problem. If I make the signs different, I can add to 0, but not multiply to a positive. If I make the signs the same, I can multiply to the positive, but I can't add to 0. And so for that reason, we would say that this one is actually not factorable. And so let's take a look then at the next one then. X squared plus 25, is this one going to be factorable? I hear a lot of you saying no. Why? What about this particular expression tells us that it is not going to be factorable? So I heard people say the fact that it's positive here. And so it's just like the last one. And yeah, that's exactly what we're going to be seeing. The fact that it was plus means that it doesn't work. So already we've seen a little bit of a rule here, where when it was minus, we were able to do it. But when it was plus, we were not. Okay, so then take a look at this last one. The last one, it's minus. Okay, so then we should be able to do it then, right? Because we were able to do the first couple where it was minus. So then it would be 1 plus and 1 minus, right? What would those two numbers be? Yeah, that's where things get tricky. Because up here on the top ones, we said basically what number times itself would equal 9. Notice the 3 times the 3 gave us 9. Or to get 49, we are saying what number times itself equals 49. That's why we were able to do that, because in order for us to add to 0, it has to be the exact same number, just opposites. So one positive and one negative, but otherwise the same. Is there any number that multiplies by itself to get us 17? No, at least not an integer value. If you want to go a little crazy on it, you could get into like root 17 or something, but you don't need to do that when factoring. Factoring, we just stick with our integer value. So this one would also be considered to not be factorable for that reason. And so you can see we kind of developed a general rule here that when factoring this type of expression, we can only do it if we are subtracting a certain type of number, like 9 or 49. What do we call those types of numbers? Yep, the perfect squares. We've been working a lot with the perfect squares recently, right? And here they are again. And so if we are subtracting a perfect square, then we can do it. Now, how else would we describe all of these expressions? Because they all have the same kind of characteristic, right? What's the biggest exponent in each one? So yeah, they're all x squared, so the biggest exponent is 2. What do we call any expression that has x squared in it? Yeah, it's quadratic. And so all of these are quadratic. So here we are just specifically looking at how we would factor quadratic. You notice that all of these have exactly 2 terms in them. Not the 3 that we sometimes would see, like if we are doing x squared plus 5x plus 6 or something like that. That one, notice we weren't trying to add to 0. In all of these, we were trying to add to 0 because there's exactly 2 terms. Do you remember what we call one of these things that has only 2 terms in it? Well, if you don't, the good news is that that's exactly what we're going to be looking at today, is a little bit of vocabulary with this. Because each of these that we started with today is actually what we would describe as a quadratic binomial. Well, really, there's all sorts of different types of expressions that we can get. You can have cubics, and you can have quartics, and you can have binomials, and trinomials, and monomials, and things like that. And we really do need to know that vocabulary. So that's what today's lesson is about, is getting this vocabulary down. So please go ahead and take a minute or two and write this into your math notes. All right, now this is the first of 2 sets of notes about the same kind of stuff we'll be taking down today, but there's something that's kind of incomplete about this that you might be wondering. And that is, what happens if the degree is more than 5? Like, what if we get up to degree 6? Do we need to know what that is called? And, well, technically there are names for 6 and 7 and 8 and all of them that go past that for any possible number. At a certain point, it stops being worthwhile memorizing all these various little Latin roots and stuff like that used to do these. And so, instead, once you get above degree 5 polynomials, I'm going to be okay if you just say that, like, degree 6 is a degree 6 polynomial. You could actually just say that it is degree 6. And of course, degree 7 would be degree 7, and so on. And then you'll notice that I was describing these as a degree 6 polynomial, because we're talking about degrees of polynomials here. You know what I'm talking about when I say polynomial, right? Well, I hope so. If not, well, that and a few other specific types of polynomials also need to go into your notes. This is the other page of notes that we're taking today. Everything else is going to be using it. All right, so you got a little bit of vocabulary in here. The foundational piece for these is a monomial. Monomials are things like x, or 5x, or 5x squared, or 5x to the 20th. Anything like that is considered to be a monomial. Now it becomes a polynomial when we have that, or we even start adding other things to it. Like if I add 3x squared to that. That's a polynomial with 2 terms. I could even subtract here because, remember, subtracting is the same thing as adding a negative. So that would still be considered a polynomial. In this case, it would have 3 terms. Or I could even make it have 4 terms. Basically, each time you keep adding another monomial, that is another term to it, then you get the polynomial. Now notice, though, that every single one of these monomials, that's the term. Okay, so when we talk about terms of a polynomial, they're the individual monomials that are being added or subtracted together to get there. But what if you end up with something that does look like this? It has, say, 4 terms in it. We know if there's 1 term, it's a monomial, 2 is a binomial, 3 is a trinomial. Do we have to worry about like quadnomials and all that kind of stuff? No. And so what do we say if it's got more than 3 terms? Then you would actually describe that as a polynomial. So you just use the general term polynomial, and you'd say how many terms it has. So you'd say a polynomial of however many terms. So for instance, this one that we were looking at up here, this is a polynomial of 4 terms. And so that's kind of your generic way once you're above that. Because again, we don't want to have to worry about all these very rarely used vocabulary pieces as we go forward. Monomial, binomial, and trinomial are the biggest ones. Now, we're talking about what can make up a polynomial like that. And so I was making up this example up here. And so you can see that I kind of wrote that example on the fly there. And that is a polynomial. And what makes it a polynomial is that we just kept adding and adding, and we ended up with, 4 different terms all added up together. But what if, because I happen to write it on 2 lines, what if that wasn't actually just a continuation of the same line? What if you're actually looking at something like this, where there was a big old fraction in there? All of a sudden, there's division taking place within this as well. When that starts happening, it's no longer a polynomial. That's why we say that it is a monomial or a sum of monomials. If you start dividing in there or something like that, then you're probably getting out of polynomial territory. That's actually something that we're going to be looking at later this year up here. This is what's called a rational expression. And yes, we will get there, but not today. Today we're just looking at categorizing different polynomials using the right vocabulary. And so let's practice a few of those. We're going to do these 3 examples together first, and then I'm going to have you do a few on your own as well. Go ahead and take a moment and write these 3 down. All right, so for the first one, we need to first categorize it by its degree. Degree always comes first. So remember, degree is the highest exponent. What number is the highest exponent in number 1 here? Yep, that would be the 3. And so we say it's a degree 3 polynomial. Now we do have a name for a degree 3 polynomial. What do we call a degree 3 polynomial? Yes, it is cubic. So we find that in our notes there. And then the second part is classifying it by its terms. That basically just means by the number of terms. Now in this particular example, I'm going to see a term here. The 8x cubed is a term. And then this negative 5x, because it's subtracting 5x, that is also a term. So there's a grand total of 2 terms here. So if there's 2 terms, what do we call it? Yep, that is binomial. And again, that's in your notes there. That was the second set of notes. So you would then describe it as a cubic binomial. Notice we do always write it in this order. I would never say binomial cubic. It is a cubic binomial. All right, so then on to the second one. The first thing we do is we classify it by its degree, which of course is the highest exponent. In this case, as I take a look through them, the highest exponent here is the 2. And so this is degree 2. This is actually something we're fairly familiar with though, right? We've been dealing a lot with these. In fact, we spent the last 2 months working with this type of equation. It is a quadratic. And so you're going to say it is a quadratic. And then we look for the number of terms here. And so the 6x squared, that's a term. The plus x, that is a term. And the plus 10 is a term. So notice, I'm looking to see what is separated by addition and subtraction, basically, for counting terms. And in this case, then, there are 3 terms. Therefore, our quadratic is a trinomial. All right, and then we go on to number 3, and we classify number 3. And I want to give you a hint here and see if you can figure out why. Number 3 is not a linear trinomial. Can you figure out why? All right, so based on what we're seeing at the moment, it would be a linear trinomial because the highest exponent here comes from these, and that is a 1 that's hiding on that. So yes, that is degree 1 by looking at that part. However, notice there are 2 terms that have the x in them. So the very first thing I should do is actually combine those like terms. We always need to simplify first before we can really classify what it is that we're looking at. Because these classifications are going to tell us what the graphs do and a bunch of stuff like that. So if I do 4x minus 4x to simplify it, notice those just become 0. And so we simplify it down first to become just negative 7. This is what we're actually going to be classifying. And so now I'm going to classify negative 7. First of all, we have to go by the degree. What is the degree of negative 7? Yeah, because if there were an x there, the x would be to the power of 0. And of course, we don't need to write it when it's x to the power of 0, which is why it's not there. But that means our degree is 0, which is why, yes, it is a constant. This also tells you why degree 0 is called constant, because notice that negative 7, no matter what I said x equaled, it still equals negative 7. It equals a constant value. Now, we do also need to say, like, the terms. How many terms are there here? Again, remember that I'm looking at my simplified form, so there's only 1 term. So it is a constant monomial. Although, as a side note here, every constant will be a monomial. Technically, we can kind of get away with just saying constant here, but I don't want to build a habit because it's a unique one in that way. It's the only one that you could actually describe by just a single word like that. So yes, I'm going to have you actually write constant monomial there to remember. Because you can never have a constant with 2 terms. For instance, I might have 5 plus 4. Yes, that has 2 terms. But remember, I'd have to simplify it first before I classified it. So if it's a constant, it will be a monomial. That also explains why our original thought up here that we might have had about this being a linear trinomial is actually impossible as well. It turns out that if it's going to be linear, it'll never be more than a binomial. And you can actually play around with some examples and see why that would be. So now that you've kind of gotten the hang of it, go ahead and take a look at these 3. And please classify each of these polynomials by degree and terms. So on the first one, we look first for the degree, which is the highest exponent, which trips up some people every now and then. Your highest exponent here is the 7. Now, typically we write the biggest exponent first, but in this case we didn't. We still got to grab whatever the biggest exponent is. Oh, and no, it cannot be simplified. These are not like terms, so we can't add them for that reason. So then, this one's going to be degree 7. Notice degree 7 is not in our table, so you'll just say degree 7. And then there are 3 terms, so it's a degree 7 trinomial. All right, so then on to number 5. You can see here that our degree is going to be 3, so it is going to be cubic. And there are a grand total of 4 terms. So we'd say that this one is a cubic polynomial of 4 terms. Because remember, anytime you're over 3 terms, we aren't going to say like quadnomial or anything like that. You can just say a polynomial of 4 terms. Now, just got a little side question here. Could I have a cubic trinomial? Is that possible to have a cubic trinomial? Yeah, we could. Like, for instance, if I were taking a look at this one, and all of a sudden I decided that I was going to try to make the 1 disappear. So if the 1 wasn't actually there in this problem, that would be a cubic trinomial. Sometimes people think, okay, well, but isn't there still like this invisible 0 there? Well, there kind of is an invisible 0 there, but if it is a 0, we don't count it as one of the terms. We only count it if there's actually a value for it. because yes, these will be affecting facts that we know about the way that this equation actually behaves, especially when you get into graphing these sorts of things. And yes, you will actually be learning, not this year, but in future years, next year specifically, how to graph something that looks like that. We're just laying some of the foundations for some of that work this year. All right, and then for number 6, I will tell you that number 6 is not a degree 9 polynomial of 5 terms, because of course we can simplify it first. So always look to see what you can simplify first, and that means combining like terms. So remember, I can only combine the like terms if they have the exact same exponent. So you see I have a couple of them that are x to the 9th. I also have a couple that are x to the 5th. And so I'm going to combine those. Notice that the x squared term is going to be unaffected. Well, the x to the 9th terms, if I do 3x to the 9th minus 3x to the 9th, that part's going to give me 0. That's just going to go away. However, the x to the 5th terms are not going to go away, but they will still need to be combined. So when you go ahead and simplify it first, you end up with negative 4x to the 5th plus 4x squared. This is really the polynomial that you are now classifying. And yes, we do need to simplify it first. Otherwise, we could rewrite the same polynomial and classify it by any different method, just by throwing in extra terms just for fun and things like that. So that's why we always got to simplify. So now that I've gotten to this point, I can see that it is degree 5, and then there are 2 terms. And so that is, yes, a quintic binomial.